Host. Who else? Ayush.
Done,
Okay,
ready.
awesome. Um, okay, so are we good, Ankush?
Yes, yes.
Okay, awesome. Hello, everyone. Welcome to the eighth OTC talk session. We have Rishit Dugli here, who's going to be talking about how we simulate the world. It's going to be an interesting talk. He's given us a glimpse of what he's been working on over the last few months. We always get some small updates on his project, so it's good to finally kind of get like a holistic overview on his projects. So let's get started. And over to you, Rishit. Please introduce yourself, and then you can you can start your talk.
Oh, can you hear me well?
Yes, I can.
Nice. Okay. Let's start. Okay. So, yeah, I, I was thinking about what I should talk about, and I think like when I was thinking about this, I just thought it would be nice to talk a little bit about a bunch of things. Because as soon as we start talking a lot more about one particular thing, um, we might lose some people, and we probably don't want to go into a lot of the details and the very specifics, though that is all of that is very interesting. So I did so I picked like a super broad thing which is how to simulate the world, um, in the hope that you can use some of these ideas to make your own world and simulate that. um, Okay, so I'll talk about a bunch of things, but most importantly, like just stop me if there's something which isn't clear, or if I
Got it.
use a word which isn't clear, or so on. And feel free to like ask me questions in the middle as well.
Awesome. Thank you.
Yes. Okay, so I guess like first let's talk about the world part of it. So what can we call a world? And I think all of these do a good job at showing some parts of a world, uh, where you have like a cat playing something, or a few people fighting about something. Um, and and one of the things that's actually quite common is there's a bunch of things moving around in all of these worlds, which we see in real life as well. A bunch of things do move around, but the the camera can also move around. Uh, and for the most part of this, let's not worry about is the camera moving around, is there something actually moving from the frame of reference that you have. And let's not worry about all of that. Let's just think about everything from our perspective, which is a bunch of things are moving around. Uh, it could be like you who's moving around, or from your frame of reference something else looks moving, and all of that stuff. One more thing that you probably can notice is when you see like all of these cat videos or these videos, um, these are the left one at least is an animation. So two frames in the animation are not really synced up because some artist sat down and created these frames. So those two frames actually have a big difference between them. You don't see it because everything like plays so fast, but in comparison to these other videos, which are AI generated, by the way, uh, you often have like a lot of difference between the frames for these animations. But even in this case, I'm I'm reasonably sure that some of you might be able to make out the red and blue thing in the bottom, um, which is just to say that you're probably perceiving things as two characters moving around. You don't perceive it all as a bunch of random colors. You most likely think of it as there's like two characters moving around. Um, and some of this is thinking as well. Not all of it is perception, but a lot of it is perception too, um, which is you fill up a bunch of things by doing simple reasoning, which is why you're able to make out the continuity. And then because of all of your prior knowledge. You know this is what a person looks like. Um, so then you're able to make out that these are actually two people. Yeah. Also, as it turns out, uh, yeah. Also, as it turns out, you don't. It seems that we are very robust. We can still make out stuff like a cat playing a violin, even though we haven't seen a cat playing a violin, or maybe some of you might have heard. Uh, but yeah, I can still like make out this stuff, even though I haven't seen it. So there's a fair amount of generalization that we can do, even though I haven't seen similar videos earlier. Okay. And uh, yeah, let's then talk about simulation. So, for now, what I'll do is there's actually one more thing about the world. For the most part, uh, and this is also quite related to simulation, which is if you see like all of these bunnies dropping, um, all of these were simulated on my computer. Um, and my computer is first off like discretizing this bunny as a bunch of tetrahedrons in 3D. So you have a bunch of tetrahedrons, small tetrahedrons all the place. And then you move those tetrahedrons. You don't move the entire bunny. And then there's also some time stepping happening, which is um, which is which is in the real world you can do a lot of substepping, which is I may be seeing like 1 second, but if I had some way, if I had a camera which had more shutters, I could probably capture something. I could probably capture all of the intermediate frames that I lose. Um, and because I'm also talking about capturing, there's a bunch of things that happen in capture which are not quite capture, because whenever you have a phone camera or any camera, it you interpolate a lot of information in between. So because what usually happens is as a very quick aside, because we might often get bogged down by this and generation and simulation. But as a very small aside, most of the cameras that you use are something called like this CCD cameras. And what these CCD cameras, the way they work is, uh, m- at least most of them, they usually have three different sensors. They have three different prisms for red, green, and blue. And then one of your prism, what that does is it takes a bunch of light in, and then it only allows the red portion to pass through, and one more that only allows the green portion to pass through, and so on. So you take a bunch of these prisms, get a bunch of light that's coming onto those prisms, and then at a given point you only have the red prism or the green prism or the blue prism. So so every so-called pixel that you see is is a value. Uh, it's either red, green, or blue. You don't have mixing of these colors, and then all of these algorithms do interpolate stuff and do a bunch of processes to make it seeable in the way we see stuff. But apart from that aside, there's one more thing, which is as soon as we talk about things being captured, we often think of them as being pixels, which is you have like a certain square, which is a certain color, or in 3D, you have a certain cube, which has certain properties like opacity and um, certain colors and so on. Um, but when we talk about the world, for the most part, unless you have tried seeing a bunch of physics that I don't understand, but exists out there, for the most part, the world is continuous. Everything around us is continuous, um, which is which is to say that if you ignore some parts of physics that I don't understand well, then you can infinitely divide things. There's always a smaller and smaller length. There's always a smaller and smaller time. So you could do so you could have like some of these capture at infinitely small times or infinitely small lengths if we ignore some parts of stuff. For the most part, that is true. For all of the stuff that we see around ourselves, everything is continuous. And when we get to like all of the simulation and world stuff, uh, we see it on a screen or we compute it on a computer. And suddenly everything becomes discrete. There isn't infinite, you can't infinitely zoom into stuff, unfortunately. So, um, or at least when you're doing the computation, you don't work at this continuous time scale during doing the actual computations. So what we should think about when we say simulation is is something called a prior, which is for most of simulation what happens, or even in this case of a bunny, I I have a prior about what a spring looks like, and I did like those elasticity priors. In a continuous way because someone discovered like an approximate continuous way that we can model stuff in the world. So I still compute everything as if it was continuous, but just when I do it on a computer, I have like this uh, a discrete thing that I bin my continuous stuff into, so I can view it easily or I can see it easily. I can do the computations easily, which is um, which is this bunny should have been like infinitely continuous. So something I'll call like C infinity a lot of times. You should always be able to zoom in small parts of the bunny, but now you see all of this like discrete stuff like angles, and that's because of the tetrahedrons. So we still like take all of the continuous laws and apply them to the discrete stuff somehow. And simulation happens to be in a lot of different things. You can do simulation in a lot of different ways. You can have robots, or you can do all kinds of crazy stuff with simulation. You can simulate fluids, rigid objects, deformable objects, or robots, or audio, or even stuff like electromagnetism and so much more. Um, and all of these usually work with different ways of parameterizing the world we have around ourselves. So there are different techniques and parameterizations to solve them, uh, and we don't want to bother ourselves with all of these. So for now, let's just think of what's happening in simulation is, or what we are calling simulation for now is, you start with some positions and velocities. Then you get a new position and velocity, and then you get a new position and velocity, and so on. And when you put all of these on the bunny, you make the video like I showed earlier. So let's call that a simulation. Um, and another thing. So now, if you think about it, the goal of simulation is to given some state of the system, um, and the state could be a bunch of things depending on what you're working with. For this example, the state is a position and a velocity. So, given a position and velocity, a simulator tries to predict what will happen in the future or predict what happened in the past. Any of them. So yeah, so that's at least how we can look at simulation for the time being. And usually there's a bunch of stuff um, that goes wrong because, or at least like actually it goes right, which is you can because like all of these are because the way you get from x0 v0 to x1 v1 is defined by some law that you said. So it's a partial differential equation that you'd solve to get from x0 v0 to x1 v1. So and you came up with that equation. Someone did a bunch of observations about how elastic stuff works, and then came up with this observation. So now I can make my bunny elastic. Well, and what happens with all of these is you can run it with a bunch of parameters, a bunch of different things. So there's stuff like, uh, in the case of this plant, how heavy is the plant, um, or what's the something called Young's modulus of the plant, which is like this physical property which says how much. Uh, think of it almost as how stiff should something be, as an analog. It isn't quite that. Um, so yeah. Now, how do you say like which one of the plants is correct? Even if you like to call the geometry applied these laws, um, because you can vary all of these parameters. How do you know which one is correct? Uh, and one easy way is like, okay, capture a real video, and see what's happening. And maybe that works in like some cases, but there's a bunch of caveats with it. Many things are not you cannot capture real videos for it. uh, I can't make like, unfortunately I can't make the cat play the violin uh, to make a simulation of it. So it's hard to capture a real video and then, um, in many cases, and then try to put it, um, which is also a very useful problem, but a different problem than what we are thinking of. And then you can take like this even further. Now let's just like drop a bunch of spheres. Yeah, which is the real thing. It's just a sphere. It all depends on what I want. Which one of the spheres do I want? And that for me is the real thing. So overall, let's call this like two processes. One is the what is called the forward process, or like any of these things which are like forward problems. So you have stuff like, rendering, which is, you take this sphere, which is a bunch of triangles, and then you render it to the screen, to show pixels, which is how you're seeing this video. Or uh, or another, forward process is that, you have like all of this, triangles, tetrahedrons, and then you want to say, let's simulate this. So then you use your laws and simulate it. So all of those are like forward problems. And as it turns out, they like, to do some kinds of worlds well, you also need something called, like all of these inverse problems. So so inverse problems are, uh, is often stuff like, let's see. I mean, there's a bunch of inverse problems in machine learning and vision. So one easy one is like you see a video and then try to generate next spots of the video, or you see a video and then you try to get like all of the geometry in the object. So if I saw a video of the sphere, I should somehow be able to know that it's a sphere, even though like to me it looks like a circle that's moving across time and so on. So you also have a bunch of these inverse problems, that you most likely might need to solve. Okay, I guess like, an honorable mention to solving some of these inverse problems is, think of a big number and then just keep doing, simulations and simulations and simulations, and then, make a human sit and say which one looks good. So, yeah, yeah, we can give that an honorable mention. That's a way to do stuff, of course. Um, oh, Never mind. This isn't quite playing the video, um, but it is just like this AI generated video of like going through the claw machine. and it actually ends up picking the pink bunny and just picks it up. That's all. It has like a few glitches here and there, but for the most part, it does a decent job at picking up the uh, pink bunny. Uh, and so, um, so, maybe like because we are talking about like all of the simulation stuff, we should probably think about how do humans do some of these things, and what does it mean to understand the laws of the world, or when do you say that you have understood the laws of the world so you can predict the future? It seems that we can do future prediction well if we have like certain parameters, because we were able to like make all of these drop to the ground, make these plants move around, and so on. So we are able to like do a decent job at future prediction. Um, but let's say like I'm trying to do this thing where I'm trying to simulate like a person catching a ball on a computer. Um, and what I do is I parameterize the ball by all of these things that would happen. So gravity acts upon it. There's some velocity and all of these things, right? So so that's how I parameterize the ball. I solve a bunch of equations, and that gives me the movement of the ball. So one thing to think about is if a 5-year-old can catch a ball, does that mean the 5-year-old does all of the integrals and equations in their head? Um, so as it turns out, you don't really need to understand. You don't really need to understand the exact parameterizations of physics, as long as you have a decent enough, as long as you have decent enough data, and then you try to build like this mental model about uh, predicting what things would happen, and what things would look like typically. So yeah, as it turns out, you don't always need to solve integrals to like get at this problem. You can also do it the other way around, which is try to solve like the inverse problem instead of the forward problem, you which is instead of like starting with the laws and getting to something, uh, you start with a bunch of data, uh, and then you somehow get those laws. Most likely the laws might be incorrect, but whatever, it works well. The way I think about like the laws being incorrect is because it's almost hard to guess, even if you experience gravity all day every day, since you're born. It's hard to guess what the parameterization would be. So which is why like Newton did something interesting, which is he came up with like the GMM by R square thing. Uh, so it's hard to it's hard to like come up with the right laws sometimes by just observing the typical stuff around you. Of course, if you have a bunch of data, like if I imagine if everyone at that time would have access to all the planetary data and see how planets move and see how a bunch of things move, maybe it would have been a lot more easier to come up with like this law. But from the typical stuff that they were observing, it was a bit hard to come up with this law. So yeah, it can also be hard to come up with laws if you have partial observations. If you if from your perspective you never saw the earth move, and then you are trying to make laws just based on observation of stuff around you, then you probably wouldn't be able to make a law saying that gravity pulls the earth to yourself as well, not just yourself to the earth. uh, yeah, this is another video that someone created from doing something like this, where simulation is extremely hard because of all of these parameters. But if you have enough data and you can do stuff, uh, then you can make like very very realistic things. And this is exactly why I want to start talking about some of the ways of like thinking about these problems. think about the broad problem of simulation, which is predicting the future or past. And there could be like multiple ways. There are multiple ways to do this. One is like the physics stuff that we talked about. Another way to do it is by using all of these large models and data sets. And of course, you can like merge stuff together as well. That works. That works quite well too. Like you can just somehow find ways to merge both of these capabilities. So, for So let's start by talking a little bit about very little bit conceptually about how all of these video generation models, 3D generation models, 4D generation models often work. Because they're, if you think about it, they're trying to like solve a similar problem, which is, uh, yes, you don't have like 3D objects moving around, um, but but you still have the perception of 3D objects moving around. Because if you see a video, um, you can still make out the actual objects. And if the model does well enough, um, then you directly consume the 2D output that you consume anyways, instead of like having all of these 3D things move around like we had in the bunny, which was a bunch of like 3D things moving around. Um, so for the most part, the problem that these generation models solve is a bit different. The problem that they solve is you start with you start with a bunch of noise, and then you somehow want to build something that allows you to transform that random noise into into what looks like a distribution. And what this distribution of stuff is let's just think of images. So it creates a distribution of images, which is a bunch of different images. And what this distribution looks like is it's approximately or it looks somewhat closer to the distribution of real life data. So it looks close to the distribution of real life images, if that makes sense. Okay. Yeah, probably think of it as you're trying to learn something that transforms a lot of noise that you have, so just random noise, into um, into something that you can query at any point, and that point would give you an image. So if you did like infinitely many queries from that, you'd get an entire distribution of what stuff looks like, which is high dimensional because it's an image. But you'd have like this distribution that you can sample from, and all of those have images. And if you think about it, the real world data also has some distribution. Um, there is some kind of stuff um, which might not be possible, at least the way we perceive things. So stuff like you have the triangle law in geometry, or um, or simple stuff like there should be like consistency in the geometry. So it looks well. So all of these like make up the real distribution of images, and then you're trying to make your distribution look very close to the real distribution of images. This is a hard problem because you don't really have the real distribution. If I had that, then I would have solved this problem completely. But I don't have the real distribution. I just have a few billion samples of the real distribution, or in some cases, probably more, which is I have 5 billion images, or I have billions of videos. So I have some samples of the real distribution, but I don't have the real distribution. So I need to build something that makes a new distribution that looks like the real distribution.
But why don't we have the distribution?
Because uh, because all you have is like a few images, and a distribution is continuous. So you all you have is like discrete samples of it.
Okay, even if it's a video, it's just a frame of images. Is that why, like, doesn't that make it continuous, or is that still too discrete?
No, that's
So can you give an example of a simple distribution? It doesn't have to be in the like a image or video world, but
yeah.
something
So
in physical world.
yeah, a lot of physical things usually follow the Gaussian distribution, which is
Right.
quite popular for a bunch of things. There's also like um, the exponential law, wh- which is fairly like physical. But okay, let's think of it as in English language, you use the word the or a and an the most, and those follow an exponential distribution as you go down, which is you exponentially use the first two most used letters in English, which I believe is the and an, uh, and then you exponentially use less as you go through the words in a decreasing order of frequency of usage. You exponentially use lesser and lesser of them. Um,
So
so
how
so
does this distribution help you recreate? Like,
Yeah. So, because if you think of it, this is also a similar problem that language models solve. So, think of it as like any of these generation models, right? It's not just images. We think of images as one thing. But as soon as you have like this distribution of images or language or whatever, then you can sample this distribution at any point that you weren't able to do from the real world. Because yeah, because this is a continuous distribution. So just sample at any point, and then you can get completely new data out. But that new data is from the similar distribution. It's from the same distribution, so it looks plausible. If that makes sense.
I mean, that made sense, but what does that help you do post this?
Yeah. So now you can, uh, if you're able to do this well, which has a bunch of tricks, then you're able to generate images, or you're able to generate videos, or you're able to generate natural language like language models do, and that allows you to make plausible data about the real world, um, which if you think about all of those videos, um, they end up doing this thing where because they know like this distribution, they're able to predict what happens in the future or predict what happened in the past, uh, given something. So
Yeah,
yeah,
so
go on.
sorry, is it like so essentially from what I understood till now is like you use like the inverse method to kind of learn stuff, where it's like, oh, you take a bunch of samples of real world things and put it into a distribution and try to figure out how it's happening. Um, through this way, which is like the inverse way, and not through knowing the formula first and applying that to something which is like the forward way, is what I understood. So
Yeah, yeah,
from what I understood is you learn through all of this inverse method of seeing something and deriving something from it, and then all of our use cases that we use it for, like LLMs or other things, is to create something out of what you've learned, which can be like a forward thing where I want to see a cat playing a violin, right? Like it has not created that before, but because it has learned some stuff, it can try to mash something together and create it for you,
yeah,
right? That is kind
pretty
of
much.
what my
Exactly.
understanding is. And to do this inverse stuff, you need a distribution so that it can sample correctly and learn how that thing worked. Like if you're throwing a ball, the fact that you don't have to tell it that, hey, this is the formula for gravity and this is the whatever angle or whatever, it will just see the image, the ball constantly falling down in a bunch of videos, and that's how it'll figure out, okay, the ball kind of always goes towards the ground or whatever. Like you don't have to teach it gravity.
Yes, pretty much. Exactly.
so
Sorry, Harsh, you were saying something. I muted you because you were not speaking.
oh,
And some noise coming from your end.
sorry, I am cooking. But so is it true to assume, or like, do we know this that in language world, like we are able to distribute it more accurately than in video world? Like the distribution is much closer to the like reality, but in video world we are like little far away.
That's a bit hard to say because we don't know the real world distribution, unfortunately.
We don't.
Right.
Yeah, because if you had the real world distribution, then all of your problems would be solved, right?
Uh, and they're not solved right now.
Oh no, like all of these generation problems would be solved if you know the real world distribution.
Okay. So we are just trying to fit the real world into a distribution like a Gaussian distribution that we know of, because we don't know the actual distribution that the real world follows.
Yeah, and we are not trying to fit it in a yes for the second part, and we are not trying to fit it in a Gaussian distribution. It will be some crazy distribution.
But isn't it like, so isn't it what we are trying to do, that if we get more and more data, we'll get closer to the distribution, and then it doesn't matter if it's real or not, it will feel real,
Yeah,
right?
exactly. Yes,
Yeah,
that's a good way of putting it. Yeah,
that
pretty
makes
much.
sense. Yeah.
And okay, so uh, so I guess like there's also ways to like control all of this processes, which is you do something called conditioning, which is like you condition it on something like text. Uh, if you wanted to do like text to video, um, so now when you're like going from this random noise to one point on the distribution, um, you just tell the model that it also needs to take something else into account, which could be something like text or images or whatever. And that would allow you to do stuff like text to video or text to or image to video or whatever you want to do. Um, Also, this is probably like where we lose the language model analogy a bit because language models do a bunch of other things. Um, so uh, not probably like the best to put this in the same thing as like all of this conditioning stuff that we talk about. Yeah, and there's like different ways to do this. So um, uh,
Different ways to do what? Sorry.
yeah, different ways to like learn this Gaussian distribution to new distribution, which is like the primary problem of generation.
So what is on screen right now is going from Gaussian distribution to what the stuff on the right is the new distribution, or what is
Yeah,
it? Okay.
stuff on the right is like a new distribution, and the
Okay.
green stuff is uh, green stuff is supposed to be the data distribution that we don't know.
Okay.
Yeah,
But essentially, we've learned that. So essentially, we put a video or whatever in sort of a Gaussian distribution, and then we sort of did that a bunch of times to learn something, which is kind of, I guess, the decoder. And then whatever we learned and whatever comes out of it is the distribution, which we don't know how to mathematically model or whatever, right? Or
yeah, a neural network does it somehow,
okay,
or like does it in some way. Yeah,
okay,
and there's many ways to like train these kind of models. So yeah, and all of these are like attempts at solving like similar kind of problems, um, where you have stuff like VAEs or flow models or diffusion models, um, that in some or other sense like solve this similar kind of problem. And I won't talk about how this works. So, uh, wait, okay, like let's come back to like video for a minute. Um, we can also think about like directly generating 4D, but let's come to like video for a minute. And and like think about like what is a video, and if you think about uh, one of the ways to like think about videos could be that you just use a bunch of image models and somehow try to somehow try to like move some parts of the image around, and if you do this well enough then you can get a video. So there's also like these kind of ways where you don't really need to generate a they don't really work so well, but you don't need to generate a video. You can generate images, then do a bunch of processes on top of it. Like this thing does like some kind of object detection, and then it tries to like warp images according to where you want them to move, and then add some noise, and then if you run like the generator, uh, it will remove all of the Gaussian noise, because that's what it does. It removes noise and gets to the distribution. So, so then when it removes noise, it will make like the uh, naively warped image into a good looking image that lies on the distribution. So you can also do like these kind of ways to like generate videos, and these kind of ways have also been tried for like 4D generation, which is like generate moving 3D objects. Um, and and you can also do something like what a fair amount of models use, which is generate some frames, and think of it as, at least like some of the early models used to think of like all of these individual frames you have as a 3D structure where you have multiple frames, and you make like this 3D structure from it. And then you learn this, and then your generator gives you this 3D thing out. Um, then you um, then you use all of the previous 3D stuff, which is a bunch of frames, and then generate the next set of frames, and so on and on. So which is also fairly popular way of like doing these kind of things. Where- And there's a bunch of things which need to be fixed for doing this, um, because what often yeah, I guess like let's just leave it at there's a bunch of tricks needed to like make this work well. Well, another way we can also see a video is you see this video on the left, uh, and probably like one of the ways you perceive them is there's like a scene and there's a bunch of objects in the scene. So there's like all of these objects on the right, which are in the scene at some or other place. Um, so that is also a fair way to like perceive what's happening in a video. And all of these objects are, of course, 3D objects. So you can move them around, do all sorts of things with them. Uh, and as it turns out, like all of these video models are really good to like simulate stuff, and you can probably call them simulated. But in some cases, at least right now, they probably are not able to simulate some kind of effects very well. Like this is a golf ball hitting a uh, wall, and this is not video model generated. This is like simulated with like known laws. So yeah, you can also do stuff where uh, where instead of like, because like video models currently have like some of these problems, they aren't fully perfect yet. You can also go back to like the earlier ways of doing it, which is where you have geometry and then you use physical laws to get stuff out, to get simulations out from it. So one of the things that you could do is somehow use like all of these models and generate some kind of geometries, or like some kind of objects, 3D objects, and then use standard physical laws to move around those 3D objects somehow. Or other ways you can do is like use those to do some kind of BAT simulation on all of these, on like some representation of the scene that you have, and pass that in as what I was calling conditioning earlier to the generator. So it has like these bad inputs of like simulation from real laws, but it can use those bad inputs to do like a um, decent job at like modeling some effects. Or other ways is you can add something like explicit geometry into it, which is which is a video model, ends up like generating a bunch of pixels, and usually it ends up generating like a bunch of continuous pixels. So, but which is all on like this 2D plane, but instead if you somehow added like 3D stuff inside it, so it would generate um, it would generate like these 3D worlds and moving 3D worlds, and maybe you can like solve some of these problems. So those are like ways to like or at least like not ways, but like some of the very few of the popular ways to do like these kind of problems. Yeah. Harsh.
Yeah, so there is this assumption, or I should say hope, that given enough data about something, the model, whatever model you're training it on, should learn the inherent physics or the inherent laws of equation, basically the fundamental law behind it, and then apply that law to like simulate whatever you ask it, right? So if you give it like all of the planetary movement data, it should internalize laws of gravitation, and then when I give an unexpected like planet trajectory, it should be able to predict that, right? So what do you think about, so I think within the research community there's this talk about that we might be hitting some geometric limitation, because we are even if given enough data, it's not able to like internalize that fundamental logic. What are your thoughts on that?
Yeah, I don't know. It's kind of hard to judge because there's a lot of problems with like training stuff well too. There's stuff like course of dimensionality, uh, which makes like some of this stuff even harder to do. Um, but I, I don't know the answer to it. I feel I think that with more data and maybe like some techniques to like get of like how we are getting like the supervision, if if there were like some techniques to do that better, then we could
Right, but that is like
use it.
talking about like a specific tool or specific like a tweak, right? But what about in the fundamental, we have reached some kind of geometric limitation that, I don't know, we might need to come up with a new math or something to go to the next stage.
Yeah.
So
No,
like,
I
okay,
don't
so
know.
there is this,
I don't believe. I don't fully buy that. I
you don't buy
I
that. Okay.
yeah uh,
Why
I
is
think
that?
that's
Like, why
partly
don't you buy that?
yeah okay. I think like that's partly true. I do think we like need new methods for like certain things, and there are still like unsolved problems. But um, to me, it doesn't. It di- to me, if like some of the problems of the ways we get supervision or like those are improved, which maybe need new methods, and uh, then I think like the overall framework makes a lot of sense to me. At least that's the way I think of it, which is like the simple thing of
So,
learning from data. That makes a lot of sense.
right. So if this method makes sense to you, then to reach to a like a stage where you can't find a difference between like AI generated video versus a real video. What do you think is the path? Like more data?
No, I so it's a bit hard to predict it, but what I'm betting a lot on with what I'm trying to do is probably like one of two things, uh, which is have like models generate axioms when they observe the world, and then have them generate like hypotheses. So you have like all of these axioms and hypotheses that the model generates, and then have those axioms and hypotheses um, be represented on some
I
like
see.
learned implicit structure, and
Hmm.
then use those to like keep doing some kind of generation prediction or whatever you want to do. And the
I
way and the reason I think of like these kind of methods is because I think it's a bit different because when you generate hypotheses, you end up generating or at least the way I think of it is, you end up generating a lot of possible outcomes that happens, or like a lot of possible reasons to explain hypotheses, uh, to
hmm.
explain the axioms. Sorry, uh, then and that probably like makes it uh, a bit more uh, doable to like understand stuff well. Or yeah, at least that's like what I think about, which may be wrong.
No, but I mean, isn't that what is currently going on, right? Like, I mean, at least from my understanding, feel free to correct me, but like as you said, right? Like first it's running things and it internalizes stuff, right? So it doesn't tell us what the axiom is probably, but it creates its own understanding, right? Which is quote unquote the axiom that it creates for itself, right? And based on that, it's giving these images of a golf ball hitting a wall, which shouldn't look like this, but it has some axioms clearly internally that has built, which makes it generate this, right? So isn't that already what is going on? So then how do we as Harsh said, right? Like, how do we get this to work better, right?
Yeah, in some sense, I guess you could think of it uh, because what it's doing is like making a bunch of rules about what how things are. Um,
Yeah.
but uh, the way I was thinking of it was a bit different, which is you can like observe the world around yourself, and then by doing like this axiom hypothesis stuff, you can understand that what kind of stuff you haven't observed and try to then explicitly go and observe the particular thing that you need to make like the next set of axioms and hypotheses. Um,
Okay.
and
So
one more
is kind of
nuance is
okay. Yeah.
and one more nuance is about like structure. Um, so I also want like the structure to be learned, which isn't quite done
What does
so
that
well
mean?
right now. So structure as in many things have like a 3D structure in a certain way, which is tetrahedrons or like some other ways of representing 3D stuff. Or video models don't really have like this kind of structure, but people are trying to add structure into it.
What
And
would that
and I
be?
wanted to like learn the structure as well. So
Like, what would knowing the structure of a tetrahedron do? Like, I mean, like it already knows the structure, right? Like, what do you mean?
no, structure is like ways to parameterize stuff.
Okay.
Um, so for
So what
instance,
is
like
like crystal structure of a material? Like what is it made of? Something like that.
no, that's no. So for instance, like one way to parameterize to put some structure in is if you represent everything with triangles. So you can have stuff like this where the dolphin is not just a bunch of triangles. So that's like one kind of structure.
Yeah. So
Another
yeah, yeah. Another, yeah. Sorry.
another kind of structure could be all of this stuff like have a bunch of Gaussians out, and those represent the board, and so on. And then there's like all of this triplane stuff as well, which puts in some structure into the generative models. As so, yeah, I call like all of these ways of like parameterizing intermediates or outputs as like some kind of structure,
So
which
from what you mentioned before, essentially the point is that we with certain things that we know that are going wrong, we just have to provide more data about those things so that it becomes better at those things that it's failing, and then it'll become better at doing other things as well, and then we'll figure out what it sucks at and we fix that as well. So essentially, it's less about changing the model and more about just giving it more data about things that it doesn't know.
hmm, I guess like that's one part of it. Yes, which I think is needed.
Mm-hmm.
But if you, but I also think like if you do this axiom hypothesis structure thing properly, then
Mm-hmm.
you also change the way the model works.
Okay.
It oh,
Yeah, it's
which I don't know what it looks like, so it's not super precise.
Okay.
is it fair to say it's reframing how you view the problem?
Yeah, I think so. Yeah.
So
But again, it's just like
then
an hypothesis. I don't know if it's true.
right. So how many how many times you should you try to reframe the problem? Like I don't know. I don't know. Like how many let's do this. Like how many ways are there to reframe the problem? So you suggested one which is like hypothesis axiom type of thing, and then what currently exists, which is uh, I don't know how to put current one.
Yeah,
Like
yeah,
basically
yeah.
you give it history, like you give it you make it generate text or something, like generate the past and future, something like that.
Okay, you know what? Let's have Rishit continue, right?
Oh yeah,
Let's
yeah.
let's let's uh, let's continue with whatever you wanted to talk about, right? And I think we'll keep the questions a little lesser for now. I think we have questioned you too much during the talk. We take it up after.
Okay. Yeah. Uh, okay. Uh, just like a one sentence answer to like the last question that Harsh asked. Um, I don't know. Maybe there's like too many ways of doing it, and I think like it's all just based on if you can like think of a way, try it out, does it work, or what's. So yeah, I don't know the answer to it. Probably there's like a bunch of other ways in the future.
That's okay.
Yeah, I.
That's fair.
Okay. So I guess like next up, there's like some of this. If you want to put in like explicit or implicit 3D structure or 3D geometry into it, then you can take triangles and represent stuff with it. But what's more popular these days is take like all of these Gaussians. So on the left, what you're seeing is like one Gaussian, which is an ellipsoid almost, and it has some color and so on. Um, and then you take multiple Gaussians together. You take like three Gaussians together. Then you, and that creates a different looking thing than what you had on the left. You take millions of Gaussians together, and that creates a different looking thing. Uh, and all of these are like ellipsoids, right? You see like all of these small ellipsoids. So um, Gaussians usually have infinite support. Um, and what that means is like you can like evaluate Gaussians at any place. They're not like a fixed size. So the ellipse is like a wrong thing about it. It just like fades out. There's no like strict clamp. Uh, so it just like fades out and so on. So that's what like all of these Gaussians look like. That's what millions of Gaussians look like. You do a bunch of stuff like give all of the Gaussians, apart from just color, give them some properties and all of it. Then you can represent 3D geometry very well with millions of Gaussians. Um, so uh, and this is also like one of the uh, other popular techniques of like parameterizing 3D structure that exists in the world, which is you start by like taking a bunch of images, you make like this point cloud somehow using tools. Then you initialize like random Gaussians on all of these point clouds, uh, and then you do something called splatting, which is you take all of these Gaussians and conceptually think of it as put them on a canvas, splat them on a canvas, and that gives you images from multiple angles, whatever angle you want. You can put the canvas anywhere, splat it on it. So that gives you like these images, and then you do a bunch of optimization. Um, so you move around the Gaussians, you make Gaussians smaller, you merge Gaussians, all of this stuff, and finally that gives you a good-looking 3D scene, which is under the hood just composed of a bunch of Gaussians. And there's also ways to like do this with nerves now, which are a bit popular, not so much right now though, where where you have like a neural network, and then you can ask the neural network for like any point in this case this cube. So you give it the coordinate of the point, and then it gives you what's the color and density at that point. So if you can do this many times, then you can make a full 3D scene. So these are again like different ways to like encode some kind of uh, geometry or like some kind of 3D structure, and we can also use one other way which is more relevant to like the kind of simulations we were looking at is 4D Gaussians, which is instead of like all of the Gaussians, instead of like all of the Gaussians being like something in 3D, you make them be in 4D, where like the fourth dimension is time. So they can also change in time. It's just another axis. Or what's more popular is stuff like this, uh, where all of these are Gaussians. But what these Gaussians do is like you have the same set of Gaussians and they just move around. So instead of like having each Gaussian be four-dimensional, you have 3D Gaussians that move around based on where you are. And yeah, you can see like the camera moving, so it's like 3D as well. And um, so this is also one of the ways to like parameterize like all of these simulations, right? Uh, because this is also a simulation. Um, in this particular case, what was happening is you used all of these techniques to reconstruct like this 3D structure, and then you put like all of this 3D structure into like the machine that allows you to take laws and put out simulations. So then you modify this 3D structure based on those laws. So try to like mix some parts of it, and there's like a bunch of other ways to mix things as well. So yeah, and I
What
guess
is the difference between 3D Gaussian with time dimension and 3D Gaussian moving?
yeah,
Is
yeah.
it
So
like it seems like same thing to me?
yeah, with all of these like 4D Gaussians and the ways to parameterize the world as 4D Gaussians, the Gaussian itself has like a fourth dimension. So, um, but with all of these 3D Gaussians, it's the exact same set of Gaussians, and they don't change at all. You just are allowed to move the center of the Gaussian to some other place. That's all.
Oh, I see. Okay, thank you.
Technically, you are allowed to deform the Gaussians as well, but let's leave that. So technically, like you can change the shape of the Gaussian a bit as well, based on something called deformation gradient. But that's like let's leave that out. Yeah, I guess like one of the reasons that you would want to do all of this is to do like some capabilities that current video models can't really do, and to get like some kind of control that current video models can't do. So in this case, this was actually a grape that I took a photo of myself. Uh, and then I put in like one grape falling on the ground or three grapes falling on the ground. And video models can't currently like do this kind of stuff well, but also they currently don't. Um, but they also currently don't have. But they also currently don't have ways to do control very well, which is it's hard to like get it to do exactly what I want. Um, so the conditioning is also a problem. And finally, it doesn't have like all of this explicit 3D structure. And maybe that isn't a problem, but currently the case is because all of these 3D generation models, all of these generation models are expensive. So if you have like some kind of explicit structure, you can do stuff like rendering very fast and have tools to do that. So I guess like that's the three problems. But more and if you think like most of them look fixable, then yeah, uh, there's like ways to or like people are trying to like fix all of them with like video models. Where yeah, this is the way like a lot of things work. And finally, like I want to talk about a little bit about like priors and when do you need explicit geometry. So I guess like one reason you'd want it um, is the stuff that we were talking about, which is like it's fast to render it. There's a lot of control because if I have explicit geometry, I can manually move stuff around if I want. I can also, so I have a lot of control on like the final output if I want. Um, so that was pretty nice. Um, but but I'm still encoding like a bunch of priors. So I guess at like some point you think of it as like what amount of priors are enough and what priors should you encode, um, which is like how many human observed laws do you want to encode in it, or how many things do you want to like force in the model, um, which is a hard problem to think of. So for instance, stuff like AlphaFold is a really good example of it because AlphaFold did like this thing where they encoded very few things as priors, almost nothing as prior. They let the model figure out stuff like 3D geometry as well and all of that, and that worked really well for them. So they had a bunch of problems. It was very hard to train like AlphaFold, but yeah, they do still don't encode like some of these priors. Uh, so yeah, it's probably like something to like for everyone to think of. Like, at what point do you say that, oh, these are human encoded priors, so they must be good? And at what point do you say that um, humans can, that like with all of this data, you can probably do a better job than humans at finding these priors? So I guess that's like the big thing to think about with like all of these video models and all of these models with like some or other kind of explicit geometry in them. Yeah, that's pretty much a little bit about what I wanted to talk about. Yeah.
Very cool stuff. It's quite interesting and thought provoking.
Yeah, definitely. And it's good to see some of the stuff that, like everything being tied together, right? Where you've been showing us a lot of these clips, like the rabbit, the bulldozer going through the trees, the small plants falling, and a bunch of other clips that you've kind of been doing. It's good to see all of it kind of being tied together, and being like, okay, this is the high level understanding of what I am trying to do and how simulation really works at a 10,000 feet from a 10,000 feet view. So good to get that. And yeah, thanks for agreeing to do the talk. Definitely appreciate you for. I know you have been crazy busy with travel and other deadlines and everything else. So thank you so much for agreeing to do this, and also a big shout out to the OTC team who's been working to get the poster out and site and messages and publicity and this and that. Loads of things have been going on behind the scenes as well. So big shout out to the team for working on that as well. So yeah, thank you so much. We'll be back next month with another talk. And yeah, hope to see you all there as well. So thank you so much, Rishit. Appreciate you. Enough. Yeah, if anyone has any questions for Rishit or anything like that, just let us. You can unmute and ask him.
I have few questions.
Yes.
So, like the method you showed about the grapes, that look really cool. Uh, what are like, are there any method which came out as like that people want to try at scale? Like I'm imagining this is like, controlled experiment with like few things. I might not have tried at scale.
Wait, what? What is the question again? Like what? Like what is the question? Like at scale? What method at scale? Are
Yeah, what like, so amongst these methods, so one of the method, the grape method, right? So I am assuming that there are multiple methods like such to simulate different kind of objects,
hmm.
and they are focused in their category of objects, right? So,
Barabar.
uh,
The niche.
right, yeah, the niche. So is there any method that stands out which might work at scale, basically?
Generally.
Yeah.
Yeah, I at least like I don't know of something that works across all kinds of simulations, because if you think of it, when you think about like all kinds of simulations, there's too much. There's like audio simulation, thermal simulation, fluid simulation, these kind of like deformable simulations, um, and so much more, right?
Yeah.
And there's different ways of like um, a fair amount of it can be unified in like um, similar ways of simulating stuff, like some stuff called like Hamiltonians, which allow you to simulate a lot of these things, uh, as well as like stuff which is um, as well as stuff which is like not Newtonian or Einstein physics as well. Uh, so there's like, of course, there's ways to do that, and those have been like reasonably successful. A lot of people have tried like all of these Hamiltonian ways. If you think of like all of this research that's happening in like um, in like all of these non-Einstein ways of like doing physics, then most of like them use like these methods. But I guess like what you're trying to ask is oh, oh, so I guess like those are the ways. But from another thing that I got from your question, it's mainly about like all of these learned methods to do like the kind of stuff that we talked about, and those people that and those works that are being done are not like any of the learned methods. They like directly encode all of the law. They do like all of these standard forward processes, forward solve all of these like standard forward problems, which are immensely important because for the most part, forward problems is what makes your phone and mobile all of it work. um, but I guess like the second part was about doing it in like the way we mentioned, like have like some inverse problems that we are solving from the data and so on. So I guess for that, I haven't really seen works that try to do like a lot that have scaled up to a lot of things. In our work, I'll share that. In our work, we did a fair amount of different objects and scaling it out to a bunch of different things. Though it's still limited to like deformable stuff. So it's still limited to solids. You can't do like gaseous simulations with it. Um, but at least like in solids, we scaled it up to like a bunch of things. So yeah, I guess that's like the state of like all of these explicit
Right.
methods combined with some kind
Mm.
of learning.
Okay.
I guess that's what like if you don't have like any kind of structure at all, like no priors at all, like in video models,
Mm.
then that's what becomes really good because you don't have any structure, so you can do anything at all. Um, uh,
But there is
which may
like,
be possible with structure too, but yeah.
how do you like control the training in a way that the model needs to care about these things? Like you don't set the prior, but then some way of steering the model, right? So you mentioned like AlphaFold like has like minimal priors they built into it, and they wanted the algorithm to learn everything. But then how do you tell it that hey, you need to learn the structure also, you need to learn the chemistry also, and there's more stuff I'm sure in protein folding. So you need to learn like these five major components, I think.
Yeah, so at least like most of these models have adopted something called end-to-end learning, um,
Hmm.
which I guess is like RL is the ultimate form of it, and no, I won't. Or in some way of thinking, like reinforcement learning is a nice way to think of it. But most of these models don't do RL. Almost all of them don't do RL. But anyway, so like all of them do like something called end-to-end learning, which is you start with like some input, you run the model to do everything that you want. It gives you the final answer. That's all it gives you. And then you, based on the final answer, you calculate like some kind of loss, and then you uh, propagate that loss through the entire pipeline. So everything is learned end to end, and everything is calculated end to end. That's like one way that people often do stuff.
Right.
this
So
kind of
comparing
stuff.
that with, I think loss function is one of the ways you can steer the model. So
Yeah.
if I if I add, so okay, so doing end to end just keep some loss, keep end to end, versus I add, let's say, three components in loss, whereas one component is responsible for checking the geometry, second is checking the chemistry, third is something else. Uh, What is the difference between two? I mean, like, is there a like a majority in the scientific community? Majority tilts towards one or the other.
No, there actually isn't a lot of these things that you tilt towards, because as soon as you add another term in the loss, that's adding another prior that you need to somehow calculate. And the first thing is, if you want to add a prior, you should have your model give you that somehow. And the second thing is, you need to find out that uh, oh, there's actually like something called geometry, and that geometry thing makes stuff look better. So as soon as you find that out, you're putting in some like human observations into it.
So
So
you're saying prior should be put in after analyzing the model's performance.
no, no, I'm just trying to say that there's no one good way to do it. Um,
Right.
People have tried like both kind of things.
Mm,
Um, Currently it seems that for the current state of stuff, it seems that doing adding finding like the right balance between priors and no priors is like the way to go. Where you still
right.
add like some kind of priors and find the right balance between it. But um, but many people, for some part myself as well, I think that we are
Yeah.
moving more towards like the thing where we don't have priors, or like gradually remove priors as like the
Gradually.
field
Right.
advances and so on.
You mentioned something about when to add priors. Can you repeat that?
Yeah, I think that's an open question. Uh,
Oh, yeah.
yeah,
Yeah.
I yeah, I don't know the answer to it. Uh, and I I have like some ways of thinking about it, but that's pretty much it. Like most of it needs to just be like tried out, and it's hard to try out a lot of things. So yeah.
Okay, fair enough. Okay, I think we can stop the recording there, and yeah, we can continue on with catch up stuff. So, Ankush, let us know.
Thanks a lot, Rashid.
Yeah, thank you,
Was
Rishit.
Yeah,
super fun.
yeah, thanks.